Hello, everybody. Great to have you here. Feel free to say hi in the chat, especially if you're new. As always, let us know where you're coming to us from. We're going to get started momentarily. Not a lot of announcements tonight. We're going to build a lot on what we've done before. So there are a lot of opportunities to kind of pause and have opportunities for me to ask you questions as we go through it. So be prepared for that, because I think what we're going to talk about today is it can be pretty interactive. Just some announcements, I guess, before we get started. We have some project reminders. So our summer runs of both our Part 1 and Part 2 projects accompanying Programming for Lovers start this week. We also have our Vibe Coding Studio course that's starting in about 5 weeks. Both of those you can unlock by joining Philomath. And if you join before June the 1st, that's going to be the close of our founding member status. So we'll have kind of a special ring of honor for those members who join before then. And the other thing I guess I would say in terms of announcements for this course is that our parallel programming practice exercises are out. They accompany something called sandpile processes, which actually are connected to one of the projects that you can do that accompany Part 1 of our course. And strangely enough, this process is very related to forest fires. So the idea is that we have a bunch of coins or grains of sand on all the squares of a board. We have a simple rule that tells us how we can topple those sand piles around the board. And the patterns that we get, as often is the case in this course, from a very simple rule, we get some absolutely beautiful patterns. This is a natural thing to divide over multiple cores because each core can be responsible for one part of the board. So those set of practice exercises are out. Special thanks to our teaching assistant, Mia, for getting that set up for us. And you can check that out. And of course, we'll also have some practice exercises accompanying assembly language. So the stuff that we're doing here, we'll have some exercises that allow you to check your work on what we're doing, because what we're doing is we're writing code, but we're writing code in a very different kind of way. And we'll have some exercises accompanying those too, as well as some practice exercises. I'm not going to tell you just yet what those practice exercises are, because I'm going to make you guess what they should be when we get to the end of what we're going to do tonight. All right. So last time, I think it makes sense this is difficult material, and I want to have sort of two steady streams to finish up what we're doing, because it's complex stuff, although I think there's a sense of accomplishment if you can get through this material. And I want to show you what we had talked about last time, just as a gentle review before we really start with what I'm going to cover this evening. So where we had started last time was the idea that we could write a program essentially in binary. So a binary string of ones and zeros, which we're going to conceptualize as a string of hex digits, could represent a program in a computer. And our first program that we saw was this program that is going to live starting at memory address 10. So it's easy to see that as 10, but it's 10 because it's represented in hex. So actually, technically, this is memory address 16, but we're going to represent it as 10. We're going to load into one of these special addresses that we have in the computer. This is a virtual machine we're working on. So it's like an abstracted computer, and yet the idea is on this abstracted computer, we have 16 total registers that we have access to. These registers are like storage that lives inside of the computer, whereas we also have RAM or memory that is not internal to the CPU. But all of our instructions to the computer are going to live at memory addresses, and they're all going to be 4-digit hex strings. So if I type in 81FF, everything turns blue because the program is automatically coloring that and then interpreting what it is that we want to do, we can add comments too after a hashtag symbol. And those aren't read, but the idea is the first two numbers there, digits, are hex digits representing where this lives in the memory. And then after the colon, the next four indicate the instruction itself. So we can read with the instruction code 8. The next part of the instruction code is going to tell us which register that we're reading into. FF tells me that I'm reading in from what's called standard in. Think about this as grabbing almost a command line prompt from the user or some kind of user input. And once we've done that, we can do this as many times as we like. So the next line of the program, where the program counter is going to go right after it reads in line 10, is to read in line 11. So the idea is that the program counter is proceeding one line at a time. When it looks at line 11, well, we need to tell it what to do. I'm going to tell it read in to register 2 from standard in. Then what we saw is, well, we can also manipulate these registers in some way. So what the computer is going to do is going to read in from memory, this special memory address FF, which is our last memory address, is going to store everything that's coming in from standard in. But the program is being stored also in memory at lines 10, 11, 12, and so on. That's a critical point that I've made before, but that we're going to come back to it, this idea that the memory can store things, but it also will hold the program. But once I've read in these register values into registers 1 and 2, I'm going to add them together and store the result in register 2. So I'm going to overwrite what is currently present in register 2 with the sum of registers 1 and 2. So the instruction command 1 indicates an addition. The next hex digit tells me which register is getting set. So this is 2. And then the next 2 tell me which 2 to add. So 1 and 2. And now you can see the comment that's given to us for free is register 2 is equal to register 1 plus register 2. We use this left arrow, which you actually see occasionally in programming. I think R uses this notation. But it's the same as what we would see if we see, this is analogous to something like x equals x plus y, which if you've made it this far in the course is something that probably is very familiar to you. And we know how we conceptualize this is to say whatever's on the left side of this equation is the variable we're going to update. And whatever's on the right side of the equation is going to contain the values that we want to use to perform that update. So when we see x equals x plus y, you're now comfortable to say, yes, at one point in time, that might have been a tricky abstraction, but now we think of everything on the right as values. So whatever x and y have as values, you add them together and you update the value of x equal to that sum. So now we have a 4-digit hex string that represents this same operation, but by manipulating registers that are internal to the CPU. And so we're setting register 2 equal to the values of register 1 and register 2 summed together. Again, that will overwrite the current value of register 2. Then we look at line 13, and I want to print a message to the user to say, let's print this resulting sum. So essentially we've taken in 2 integers from the user, we've summed them, and then we're printing the result. And I don't really need the registers anymore, which is why it was okay to overwrite them. But I do want to write register 2's value into a special memory address, which is FF. So that will print that message essentially to standard out to the user. And this is analogous to printing in some sense. And we can even save our program. I'm not going to do that, but we can save it somewhere to the computer, and we can also add values to standard in. So if we want to add some values, the values that we even have a nice reference. So the values that I wanted to have here are, I think the values I had were C8, and you can see what these things are. So C8 in hex, there's a nice little converter over here that tells you that that's this string in binary, but it's our old friend 200 in decimal. And the other number was 1e, which is our friend 30 in decimal, but in binary is just 11110. And those are the values I want to add. So I want to add 00C8 and 001e. And when I add both of those values, and then I go to the run part of the program, we could see standard in is contained here as 00C8 and 001e. Those have been loaded in. A standard out is going to get printed here. It's also going to get printed here. So when we look at the memory, we can see that the memory contains all these blank zeros, which are halt states if they're ever encountered. But the program always will start by convention at line 10. And when we step it forward, we're going to see register 1 gets the value from standard in. Register 2 will now get the next value from standard in. So this is a queue, a concept that we saw with parallel programming. So the next value is 001e because that's what I added second. So that gets set as the value of register 2. Line 12 says add them both together and update the value of register 2. When you add those two things together in hex, you get E6. Okay, so that's the number 230 in base 10 is E6 because it's 1e plus C8. And then the last thing we do is we take that value E6 that's stored in register 2 and we store it in FF, which is going to cause it to get printed to the console. So we see E6 printed. We're going to write larger programs here. And when we write these larger programs, we're not going to need to step it one line at a time because what you're going to see is in a surprisingly short amount of time, I hope, I'm going to get you comfortable with writing much larger programs. But we can run this and there's a step process and there's a little bit of a delay between each step so that we can watch this process happen. And you can see this, happen with some small amount of delay. Internally in the computer, this is happening according to a clock speed. So you're in the billions of cycles per second in the computer. So in practice, this is all lightning fast, but Xtoy has this nice visual way of showing you how these operations are taking place as you run the program, which is pretty good. The question, of course, becomes, if you look at our program, could we ever really do anything sophisticated with this setup that we have? And the answer is yes to that question, because after all, something that you might know and something that we've talked about previously is that anything that any computer is doing is ultimately represented as machine instructions that involve strings of ones and zeros. So at the end of the day, we're just changing transistor states. And that's all we're doing. The abstraction that is given to us by a programming language, such as Python, allows us to not have to get our hands dirty with those particular details, right? But the idea is at the end of the day, we can appreciate now that you can do something with a computer with just strings of zeros and ones. And each of these numbers here can be represented in binary very easily by saying what is the binary representation of 9 to F and F. And so if I typed in 9 to FF, we get the binary string 1001, that's 9. We get 0010, that's 2. And then FF is 1111, 1111. So we saw previously that this hex to binary conversion is actually quite easy. And so what hex is really is an ability, instead of us looking at this hypnotizing string of ones and zeros, we can represent it much more nicely as a 4-digit hex string, which is good. But ultimately, this is a very powerful concept, right? That the program itself is a string. That might not seem like much, but this idea that a program can be represented as a string, which means that it's really just a collection of zeros and ones represented as essentially a binary string of just 2 digits. That's very powerful. And that will lead us next time that we're here together. And I think the finality of what we're doing, it's going to lead us to what I call the dark heart of computer science. So it will take us to a very surprising place. But that's all for next time. For now, I want to complete this Visual X Toy virtual assembly language machine that we've introduced and show you how we can actually do something like write a function, call a function, and what is it that all of the different instructions do, because I've only actually introduced like 5 thus far. I've introduced an add, a subtract, and we can load in a value to a register, or we can load in a value from a memory address to a register, and we can also store something that's in a memory address or something that's in a register to a memory address. So we have 5 operations that we can do, and you can see over here on the right, there's a reference that tells me add and subtract are 1 and 2 in terms of instruction codes respectively. We have this load immediate that says set a register equal to a certain value. That's the other thing that we saw previously. So if I set set register 1 equal to, I don't know, the value that we had, which was C8. So that would set register 1 equal to C8. How I've done this instead is take that value from the user. So 81FF, but it would lead to the same end result behavior. But we have 5 operations, and as you can see on the right, well, there are 16 total operations. 0 is our halt. I guess I introduced 0. 0 halts the program, so 0 followed by anything is always going to halt. And you can see in the program itself, everything, if it's not set, is set to 0. So if anything that is not part of the program that we have written is encountered by default, it's going to halt the program. All good. So for now, the question becomes, what we're going to do is introduce all of the other 10 operations, and I probably should get comfortable using X and say all of the other A operations that we're going to need. What are they? For what we're going to do, some of them are vital. A couple of them are not that important, but I also want to introduce them to you just so that you're comfortable and can say that you have seen this, because it's going to really build up your intuition and make you a stronger thinker computationally. But we'll get into all this. That's our preliminary review of everything that we're going to do. For now, as always, remember to like and subscribe, join our mailing list and Discord. That's the way to stay in touch with what we're doing. And you can check out everything else that we have linked in the description for a lot of other fun stuff. I'll have opportunities for you to tell me what you think about stuff as we go. So we'll have a few little exercises and questions for you momentarily. But yeah, I think we're ready to get started. And without further ado, let's code. Is that what we're doing? Let's code. We'll give it a go. So we've introduced to this point in time a few operations that are built into this Visual X Toy hypothetical virtual assembly language machine. And it's an old program, but it still works, and it's a great illustration of some fundamental ideas in how we take a high-level language and what might be going on behind the scenes to convert this into a strings of ones and zeros that still, at the end of the day, represents a program. For now, I'd love to show you what are the other operations. And if we have an addition and a subtraction, the other types of operations that we might want to have are things that are easy to perform. If you think about the computer as a collection of lights that are on. that are ones and zeros. We want something that is easy to wire up as an electrical engineer and that is also lightning fast. So an addition or a subtraction, that's a simple building block operation of the computer. Another one, which might not seem useful to you at all, but I'm going to show you an instance of where this is useful here in a minute. But another one is to take an AND of two particular numbers. So here's another instance where computer programming, in whatever form it is in a sense inextricable from logic. And at this point in the course, I'd hope you're comfortable with the idea of performing an AND of two things. And when we have a statement like if X and Y, that means that, well, we're only going to enter that if block if both X and Y evaluate to true. And this operation has a natural kind of connection to what we're doing here with this virtual machine, with an AND operation that says represent two numbers. I've got two numbers here, A and B, as their binary strings. And then, well, if they're binary strings, we can think of one as being a light that's on, or a transistor that's in an on state or a higher state, and 0 as being off. So 1 could also be thought of as true. 0 could be thought of as false. And if that's the case, I can go bitwise, so digit-wise, and take a look at each individual position of the two integers. If my integers here are these particular strings, you'll notice C is, in this case, the AND of the integers A and B. You'll notice this position is 0 because, well, false and false is false. And anywhere where you have a 1 and a 0, so a column like this or a column like this, is also false, because for an AND of two statements to be true, we need them both to be true. Notice then, this column evaluates to 0, this column evaluates to 0, but a column like this one or this one corresponds to a position where you have two ones. So you have a true and a true. We also, if we're going to have an AND, we should have an OR. And there are two types of OR that we use. Well, there's two meanings of the word OR in human language. Most human languages don't have separate words for them. I think it's something, somebody can check me on this. I think Bulgarian, for whatever reason, that comes to mind as a language that has two different words for the two meanings of OR. Logically, OR often means, well, and how we have worked with it in terms of Python, is if you have two statements, if either one of them is true, then the OR will evaluate to true. But there's another meaning of OR, like if someone asked you if you wanted to go to the beach or the mountains for your vacation, the idea is that, well, one of those can be chosen, but you can't choose both. Whereas in programming, if two things are true, the OR of them is always going to be true. And that's how what we've assumed is the case when we've programmed. So if X or Y and they both happen to be true, great. We're still going to enter that if block. Now, the XOR is different because the XOR says if it's the case that they're both true, and here's an integer A represented as a string of bits and another integer B, in this particular position, you see two ones. In this position in C, the XOR of these two numbers, you get a 0. So you only are getting ones in the case that you have a 1 in exactly one of the two positions. So here you have 1. Here you have a 1 for B and a 0 for A. So in each of those cases, you have a 1 in that bit in that position of C. But again, if you have both of them equal to 1, that's no good. So it will evaluate to false. Another way of thinking about an XOR here is that you're flipping this light on in C precisely when the lights aren't equal. So if you see two zeros in A and B, well, the light stays off. If you see two ones, they're equal and the light stays off. But if you see a 0 and a 1 or a 1 and a 0 in either of those cases, you flip the light on in C. So it's a test for inequality bitwise. And that's why it's, I'd say on a very high level, that's why it winds up being implemented as an operation, because it allows you to do a quick check of that equality. One more thing I'll show you. Well, it's really two operations in one. And this might strike you as a little odd as to why this would be a built-in operation in a computer that only has 16 built-in operations, is to do a shift of our digits of our number. So we're going to allow ourselves to shift in either direction. In this case, we're going to shift a number to the left. So if we were to shift this particular number to the left by 2 bits or 2 digits, these 2 zeros at the front would fall off. This one would be the initial digit of the new number. All the other numbers would slide to the left 2 positions. And then you'll notice this 0 would come here. So you're going to get 2 initial zeros coming in at the right. So if you push this, shift this number over by k digits, you're going to have k zeros that get populated on the right side. We can also shift the other way. So I can instead shift over to the right. In this particular case, if I shift everybody over by 2 positions, then you fill in a 0 and a 0 here, but everybody else goes over 2 positions. And these final 2, well, it's like musical chairs, right? These 2 fall off of the end because they didn't have anywhere to go. So the final one here comes from this, which was the third to last digit in this representation of the number. I said I would give you an opportunity to think about this a little bit. So my question to you is, what is it that each of these operations, shifting the digits of a number over by some number of digits to the left or to the right, what do those represent like in an arithmetical context? What operation are they actually representing? BZ got very excited about this. Might have given us a little bit of a preview of my question, which is good. It's always good when you answer a question before I even ask it. Don, welcome. Ben, welcome back. Javier, I hope you enjoyed your vacation. All right, in this case then, if we're going over to the right or to the left is probably the easier direction to see. Because if you were thinking these aren't binary numbers, they're just base 10 numbers. They just happen to have a lot of 1s and 0s in them. If you looked at this number here and you wound up with this number here, well, you would know all I did was add 2 zeros to the end, so I multiplied by 100. Now, the only thing that's trickier here is that everything here is base 2. So because our base is 2, adding 1 0 would correspond to multiplication by 2. Adding 2 zeros would correspond to multiplication by 4. Adding k zeros would correspond to multiplication by 2 to the k. Arithmetic and this law is still preserved. It's just that the base has changed. So this operation here looks like something that's just moving bits around, but it's really just a multiplication by 4. The right shift is probably a little trickier to see, because if you imagined, well, if this were base 10 and you had this number, what is it that this number would really correspond to? And you think, well, anytime I chop off 2 digits of a number in base 10, that's really just dividing that number by 100. Of course, one of these digits could be something other than 0, in which case I've not divided it by 100, I also have a remainder, but that remainder disappears. So we're performing a division, not by 100, but this time by 4, because we're losing 2 digits and we're working in base 2. So we're doing a division by 2 to the k, where k is the number of digits over that we're going to be shifting this to the right. But that division is a special type of division that we have worked with for a really long time, which is an integer division, where we ignore any sort of remainder. So if I left shift by k digits, then that left shift is a multiplication by 2 to the k, power of k. And if I right shift, it's an integer division, so I ignore the remainder by that factor of 2 to the k. So this is all very nice because we have very fast operations that can do a little bit of logic for us. Good. But that also can do certain types of multiplications. Now, if I want to multiply by 3 or 17 or 42, those aren't powers of 2. So I'm going to have to be a little bit more clever in terms of what I do. You might start thinking about that. One thing I'll ask you right now is, okay, well, if we're performing the integer division, but when we do a right shift, so again, to refresh your memory, when we look at a right shift, in this case, we're right shifting by 2 digits. So 2 digits fall off the right side and disappear. That's an integer division where the remainder disappears. But what if we want to actually capture that remainder? So one of the things that we've seen a lot in the course is a lot of times we care about the remainder of an integer division. And if that's the case, well, how is it that we could represent something like dividing this number, and I'm not off the top of my head sure how I could quickly convert this number to base 10, but it's a 16-digit binary number, and I want to take its remainder after I divide by 8. You'll notice 8 is a power of 2, but here's an exercise for you, which is to say, first off, what is the remainder when I divide by 8? When I divide this number by 8? And secondly, when I do that, how is it that I would get that in general using left and right shifts? BC said you look at the last 4 digits. Again, it's not quite right. And there's 2 points here, which is, the first question is, where is this number %8 hiding? And then how is it that I could recreate it? So yeah, you're right. It's the last 3 digits. When you divide this number by 8, well, it would be like if you imagine this is base 10, and you divide it by 1,000, what's your remainder? It's going to be 100. So this is no different here. We just changed the base. When you divide this number by 8 in base 2, then the remainder is 100. And this is the 1's place, the 2's place, and the 4's place, so that the remainder of this number, when you divide it by 8, is 4. I don't even know, I don't have a good sense in base 10 what this number is, but I know that when I divide it by 8, I get a remainder of 4. But then how is it that I get that, right? Like, I want to use left and right shifts to actually ultimately obtain the answer. I don't want all this extra stuff. Anybody see what we do? Right shift would be division by 8. Good, but then we would lose the 1, 0, 0 at the end, right? We have a smart bunch. We got a smart bunch. The chat is very wise. The chat is wise because you're answering a question that it's the same thing. BZ really got us off on the wrong foot of answering questions that I haven't even asked. Because here, this question is much easier than what the chat has already answered, right? We want to capture the numbers that are falling off the end of 1, 0, 0. So we don't want to right shift this thing by 3 digits because then we lose the 1, 0, 0. What we want to do is get rid of everything on this side, okay? So what I'm going to do is that I'm instead going to left shift this number and push all of that stuff off the end. And then I'm going to right shift everything back. So there is a simple way to do this is left shift by 13 digits and get rid of these first initial 13 digits. And then I'm going to right shift everything back. And at the end of the day, there's my 1, 0, 0. So I get a bunch of zeros and then 1, 0, 0. Now, I wanted to ask you if there's a faster way to perform this because this requires 2 operations. And, I mean, people have made careers going back decades on being good at how is it that we do something faster with simple operations where it might not be initially clear how that works. And in this particular case, AKB tells us, why don't we just instead and our initial number A with a special number called a bit mask. So the bit mask doesn't represent anything that we care about for longer than one operation. But in this particular case, we could AND the initial number with the bit mask that's a mostly zeros and then 3 ones at the end. So those 3 ones at the end, essentially when you AND a number with a collection of ones, all that serves to do is keep a number around if it's a 1, keep a digit around if it's on, and keep it off if it's off. So when you AND a number with all ones, you would get the number back. But when you AND it with a bit mask that starts with 13 zeros, all the first 13 lights are going to automatically get switched to off because, of course, you're ANDing something with a bunch of false values. And then the final 3 are just going to be whatever they were in the initial number A. Simple but cool. And the idea is, even though AND probably didn't seem particularly relevant for arithmetic, here it is. Okay, one more question. How is it that we would represent negative integers? So BC, you said reserve a bit for it. Okay, good. So 0 could represent a positive sign. 1 could represent a negative sign, or vice versa. As long as we agree. And here's where there's like an age-old issue of you have to get all the engineers to agree on whatever format you want to come up with. And this has a lot of more advanced examples, and it connects to all kinds of stuff in computational biology, for example. Like if we have a software program and it works with evolutionary trees. So we have a concept of what an evolutionary tree is, right? But we saw this earlier in the course when we talked about we need something like Newick file format so that everybody agrees on one format that we can hand off between programs so that then I can take a look at my tree. It's the same kind of thing here. If we agree that the first digit is a 0, meaning a positive number, and the second digit as a 1 would be a negative number, great. Although then we need to agree on, well, what is 10000? Because there's actually a couple different ways of looking at this. If this is the number 0, well, what would this be? If a 1 is the negative of whatever comes after it, does that mean that this would be a negative 0? And the point is, that's one way of representing the numbers. So this would be negative 0, and we'd have to have a negative 0. And that's a long and separate story that we're not going to get into. But this number here would be negative 1 and negative 2 and so on. That's actually not what we're going to look at. We're going to look at something called 2's complement notation. So the idea of this is that, well, the numbers are going to increase up until the point where you hit 0 and then a bunch of 1s. So this is a 4-bit, 4-digit representation here. So we don't have a lot of storage. We can only represent 16 numbers, and this is a simplification, but the idea is once we hit 7 and you add 1 to that, you hit the string 1000. So it's weird to say, well, I added 1 to 7 and then I got a number that's 0, and then I'm going to go downward. That's just a little bit strange, and there are other compelling reasons for this, but 2's complement notation, the idea is you establish what your largest possible integer can be represented as and what your most negative integer is. And it's no accident. In this case, you have 4 digits. The largest number is 2 to the 3 minus 1, which is 7. Or 2 to the 4 minus 1. 2 to the 3 minus 1, which is 7. And the smallest number is negative 2 to the 3. So that's 1 less than the number of digits that you have, but it's the number of digits that's assigned to the number. So the first one is assigned to the sign. The point being is when you hit 0's 111 and you're at 7, you add 1 to it, and now all of a sudden you wrap all the way around and you're at the smallest imaginable negative number. And then as you continue adding 1, well, you work your way up again until you hit, this is going to be negative 8, then negative 7, and you keep adding 1 until you get to 1111. And that in that particular case would be negative 1, because when you add 1 to it, you get all zeros because you get overflow and you only have storage for 4 numbers. So if you added 1 to this, you'd get 00001, but that 1 isn't represented, and you're back at 0000, which is 0. So there's this nice cyclic process where everything is being done kind of modulo a remainder, but also you get negative integers being represented too. So most of the time when you're working in a modern programming language and you declare an integer, something that we've taken for granted for a long time, I set x equal to 3. Behind the scenes, it's actually represented using 2's complement notation. And that's how we're going to represent this in xtoy as well. So if we look at xtoy, and you'll notice that I have this negative 27,905 number here. It's negative because xtoy is representing any number that starts with a 1 in 2's complement notation. And, you know, the most negative number I could represent would just be a bunch of 1s, which is FFFF. Excuse me, that's negative 1 because 1 more than that would cause all of these ones to collapse into zeros. So one more than this number gives me a 0. All well and good. The smallest number I could represent, or the most negative number, would be 1 followed by a bunch of zeros. Notice it's representing it as positive numbers until I have 16 digits. And then this is the smallest value, negative 32,768. So this is built into XTOY. And so it's worth knowing. One other thing I would say is there is an actually associated with left and right shift. And that's because XTOY is viewing behind the scenes, even though these are just binary strings, it's conceptualizing something that starts with a 1 as a negative number. And so because that's the case, we might represent what is this number in base 10. And I could go and show you in XTOY, or we could do the conversion. This number is negative 40 when I convert it to base 10 in its 2's complement representation. When I left shift this by 2 digits to the left, you might remember, well, left shift by 2 digits means everybody moves over, zeros come in at the right. So this is a multiplication by 4. And yet when we convert this thing to 2's complement, it's negative 160, or in 2's complement to base 10, it's negative 160. So that's nice because we thought of this as a multiplication by 4. We left shifted it. And even if the initial digit is a 1, which means this is a negative number, we're still preserving that this is a multiplication by 4. That's really neat. That's a nice feature of this 2's complement notation that we could work out mathematically and justify precisely why it's always got to be the case. But that is certainly very convenient because we want this left shift to be a multiplication by 4, whether the number is positive or negative. If we right shift it, which is a division by 4, integer division, then the problem is zeros are going to come in at the left. But what is this number? This number is negative 40 in base 10. So if we're right shifting the number by 2 digits, that should be an integer division by 4. But the problem is negative 40 divided by 4 should be negative 10. So the actual answer should be something that starts with a 1. And so here the zeros are going to come in at the left. That's what I told you was going to happen. And that's not going to necessarily represent what it is that we wanted. So this right shift is called logical right shift. It works for unsigned integers. So if we're not representing numbers as 2's complement, we're just saying, look, if you have a bunch of 1s, that's just a big positive integer. That's okay. But if the initial 1 represents a sign, it's going to break. And so what XTOY represents, because it's trying to represent positive and negative numbers, is what's called arithmetical right shift. And in that particular case, if this leading bit is a 1, then 1s are going to come in at the left, not zeros. And if it's a 0, then zeros are going to come in. So it's going to work like this if this initial digit is a 0. But if that's a 1, which it is in this case, 1s are going to come in on the left. And I could plug this in. In fact, I will, because it's an easy one to plug in. So it's essentially 12 1s followed by 0, 1, 1, 0. I'm going to do something very fancy because the 12 1s are just 3 copies of F in hex, and the 0, 1, 1, 0 is 4 plus 2, which is 6. So in my conversion over here, I'm going to say that's FFF6. And what's nice about that is that's the string that we had. Lo and behold, that's negative 10, which is what we wanted to do. We were trying to integer divide negative 40 by 4, and now we've done it. The only change that we have to make is if this initial bit is a 1, 1s are going to come in at the left, and this still amazingly represents integer division by 4, whether this is a positive number or a negative number. I think that's pretty neat, and if you study this deeply, you see all sorts of places where conveniences get introduced by electrical engineers and IEEE. There was a meeting of IEEE where they worked all of this out to make sure that everything was convenient for everybody going back multiple decades. And we're fortunate for that. And so as a result, we don't have to think too hard about this. I just know that at the end of the day, this is my integer division by 4. So we can summarize this process, as I said, this works well. But we can summarize this as saying add and subtract followed this same syntax. So the first hex digit says add, a 1 is add, a 2 is subtract. We're also going to add 4 more of these arithmetic or logic operations. So we have an and, an or, which here is an XOR, left shift and right shift. Those are these 4 operations I've introduced. 3 is and, 4 is XOR, 5 is L shift, and 6 is R shift. So this particular instruction here is 3, so this would be an and. As we had seen before with addition and subtraction, the next 4 binary digits, or the next hex digit, in this case, which is 2, tells me what register I'm setting. So in all cases, I'm setting register D, whatever the second hex digit is. And then we're using the next 2 hex digits to indicate, well, what are we actually operating upon? So in this case, I'm taking the AND of registers S and T. In this case, I'm taking the XOR. I'm going to left shift register 2 by whatever is stored in register 8, or right shift it by whatever is stored in register 8. So the idea is all of these have the same overarching syntax. 3228, 4228, 5228, and 6228 all correspond to doing something to registers 2 and 8, storing the result in register 2, but then the 3, 4, 5, 6 is just the instruction code to tell me which of those 4 operations I'm actually executing in that particular case. This actually is an example of something that, if you followed our parallel programming discussion previously, where we'd spent hours working on parallel programming in Python, we talked about parallelism and concurrency. And we stressed that there is a difference between these two concepts. It's an opportunity for me to be disappointed by asking you, remind me what the differences are between parallelism and concurrency. How are these two terms different? And what are their definitions? And I'll explain why I'm asking this momentarily. Let's do the easy one. What does parallelism mean? What is parallel programming? Parallel programming, doing multiple tasks at once. And by at once, you mean literally, at the same time. Multiple things, literally at the same time, is parallelism. Okay, good? And so to do that, you have to have multiple workers, or you have to have multiple CPUs. What is concurrency? Do you remember what concurrency is? Because the idea is you can have concurrency, but not have parallelism. How do you have that? It's always funny because we're never going to be able to do anything in parallel. Our brains don't work in parallel, but our brains work concurrently all the time. AKB says concurrency is multitasking. I like that. And I can't ever multitask by truly thinking about more than one thing at a given point in time. Maybe at one point in time, we could evolve our brains to have multiple cores so that I truly could think about multiple different things and actually actively work on multiple things at the same point in time. I guess there are examples of like split brain patients that could write in two languages at the same time. There's some kind of example of that. So I guess there are certain ways in which you could become a parallel organism, but it's just generally not going to be the case. And yeah, so a great idea of concurrency, something that's concurrent but not parallel, is if you have a to-do list, or if you're a university student, you're taking courses, you're not in two separate courses at literally the same point in time, or you're not doing two different things on your to-do list at the same point in time. You could also have a single core that has multiple apps in progress. It's balancing these out by spinning plates so quickly that you don't notice that it's cycling between them very quickly. And we've talked about parallelism, which is literally performing tasks at the same time with multiple workers, whether they're people, CPUs, etc. And it was hard for us to like separate this idea of parallelism from concurrency, because if I'm performing tasks at the same time with multiple workers, I've got multiple tasks in progress, right? Like that certainly makes sense. But I said I would give you an example of something that's parallel without being concurrent. And there is a bitwise parallelism that is present here as well, which is that I can simultaneously change all of the bits. Like if I look at something like an and is the easiest way for me to see it. Here's 8% using an and, right? I could perform this operation like independently of any other bit. I can just do bit by bit, and all of the 16 bits that are involved in this, this position only needs to know one thing, which are the values of the corresponding bits in the initial A and the mask. And all those could be done independently. And so you have a parallelism that's inherent here that's also in, I should say, in our left shift and right shift formulation, where if I want to know this position, I really only need to look here, right? And so there is parallelism that is inherent in the operations that we are performing within Xtoy that are built in as well. It is not concurrent because there's not more than one task going on, but there's parallelism that's built into the instructions, which is pretty cool. So you get a chance to see that particular example. I think that the technical precise definition here is a little beyond what we are trying to present, but I want to give you the intuition that we're doing this essentially in parallel. So that's 6 more operations. And now we're up to, I think, 12 operations. And the point becomes, well, yeah, but how can I do anything that resembles anything like a function that we've written in the course? I'll give you 2 more quick operations. Actually, we're not at 12, we're at 10. So we have 6 more. But I'll give you 2 more for now. We talked about load. So the load instruction is 8. If I see an 8 followed by, say, a 4, I'm loading into register 4, and then the final 2 hex digits, which here are 88, tell me the memory address to read into register 4. I will quickly show you a different version of this that we'll probably not need too much of. But I also could do something very indirect, which is maybe register 8 stores a memory address. So in this particular case, it was somewhat direct, right? I said, load into register 4 whatever is contained at memory address 88 or whatever. And instead, maybe this value like 6E or something is going to be, that's the address, but it's stored in a register. So I actually have another way of doing this that's built in to say if the instruction is A, this is 8 plus 2, which is 10. So the instruction is A here. That means load indirect. So load into register 2, yes, but we actually ignore the next 4 bits. And the final 4 bits are giving me a register. So if this were register 8, you'd go into register 8. You would look and see what is contained in register 8. its value would be a memory address, and you say, oh, go and look at that memory address and take whatever is there and grab it and place it in a register 2. So you've actually seen this concept before in programming. This is on a very base level, the idea of like references. So we've talked about pass by references when we've worked with certain types of data, whether that's, say, a list or a map where it's like a user-defined class. In certain cases, you pass in a reference to a function or something to the function, you get a reference to it, meaning you can change that underlying object. It's the same kind of idea here. What is being stored in register 8 is a reference to something that's in the memory. So it is an implementation of what some languages would call a pointer. I'll leave it at that, but I did want to point that out. And then just as we can load indirect, we can also store indirect. So if I want to go the opposite direction, how I've presented store is to say it's instruction code 91001. The next 4 bits tell me which register, and then I want to take that register and put it somewhere. Before, when the memory address was 88, I was putting register 4, its value, at that memory address. But I also could say, well, instead, if it's instruction B, take register 2 and put it at the memory address that is stored in some other register. So look at register 8, it'll tell you where to put it, and put register 2's value there. And that hex code here would be B208. So A and B as the initial instruction codes are going to be things that we could use. I'm probably not going to write a lot of code that uses it. But the idea is we now have 12 operations. And all we can do is read and write from the memory, and then manipulate registers that we have read in from the memory. Grab in some values, whether that's from standard in or somewhere else. Grab in some values, manipulate them with operations, and then write them back to the memory. So our computer is not particularly complicated at this point in time. And we are left with this quandary, right? Which is, yeah, but I want to write a function. I want to write for loops. I want to write if statements. There's nothing about this computer that allows me to make that choice. When I execute a program, I start at line 10, 11, 12, 13. That's how Visual Xtoy works. The program counter just keeps getting updated. And what we really need is for that program counter to be able to branch, to take a choice based off of some condition that it tests. At one point in time, and we're talking about going back like 100 years, the foundations of computer science, this concept was like a revolutionary idea in computer science, that at the fundamental level, you can do very complicated things if you can just implement the simple idea of being able to test some condition, some state in the computer, and then making 2 different decisions or multiple different decisions based off of that state. So the concept of branching is so inherent to modern programming or modern computer science that we kind of took it for granted when we introduced the very foundations of programming. But the idea is connected to something like choose your adventure, right? Like these old books that say you can start on page 1, and then when you get to page 2, you have a choice to make. You go to page 47 or page 91. You can get a lot of alternatives, and this idea of splitting the program based off of some state is really important, and it's not something that we currently yet have in something like Xtoy. So that's what I should give you is, what are the operations, what are the remaining operations that allow us to essentially implement this control flow to test a state and then be able to make a decision based off of that state. It's not an intelligent decision, it's always a deterministic one. The program is forced to make this decision, but the idea is that it still can go in multiple different directions so that perhaps we put in different inputs and we get different outputs. The first such operation then is called jump 0. And jump 0 says the instruction is 1100, which is, in this particular case, that's C. 8 plus 4 is 12, so C is 12. The next 4 digits, as always is the case, indicate a register. So this is register 4. And what the instruction says is if register D, or or register 4 in this case, is equal to 0, set the program counter to this memory address. Jump the program counter to this location. So if we were at address 3A, for example, and address 3A said C488, and I went in and I checked register 4 and it were equal to 0, hey, that means I can jump straight to address 88. I wouldn't be going to the next line, which is 3B. So this allows me to shoot the execution of the program to some other place based off of a simple check. We're also going to have just go. So we'll have another operation E, which is 1110. 8 plus 4 plus 2 is 14, which is E. And it says set the program counter to whatever register D contains. So this allows us to say, you know what, the program counter doesn't always just have to go to the next address. Sometimes I hit a point in the code and I want to set the execution of this code to some other position entirely. Those two operations are important. I'll show you an example of it. So say, for example, we have this if statement. If R3 is equal to R4, print R3, else print R4. And I want to say, well, say R3 is a register, say R4 is a register, and then printing, remember, is storing into this special memory address FF. And how would I represent that in Xtoy? So here is line 20. It says 7526, load register 5's value to be 26. This is a very initially confusing line. I don't want you to worry about it for now. The next line we're going to, you'll see very soon, you'll see why I've done this. Line 21 says, well, how do I check equality and then make a decision according to whether these two registers are actually equal? One way I could do that would be to subtract R3 minus R4, and then if the result is equal to 0, then I know that they're equal. Otherwise, I know that they're not. So I could subtract register 4 minus register 3 or register 3 minus register 4. It doesn't matter. Setting the value into some register 2. So this is 2243. And then what I could do is check, are these two values the same? And I can check that by saying, is register 2 equal to 0? If it is, I'm going to jump to line 25. So C225 says, check register 2, is it 0? If it is, jump the program counter to line 25. So if they're equal, I would go to this particular line and I would do 93FF, which is store register 3's value to FF, which says print register 3. So that's nice. If they are equal, I will jump here and I will essentially do this part of the code. If they're not equal, register 4 and register 3 aren't equal, which means, well, when I do this subtraction, register 2 is not equal to 0, I'll instead carry on. So I'll go to line 23, I'll store register 4's value to FF, which is what we see here. The key point is I don't want to also print R3. So if I don't want to also print R3, I need to make sure that I don't execute this line, and I want to jump over it. So line 24 says jump over it until we get to a halt, or whatever other line of our program. But jump over 25, how do I know that I can jump line 25? Well, I have a jump command, it's E, that takes a value in a register and jumps to whatever that register stores. This is why I set register 5 equal to 26. This shows you that when we program in Xtoy, we have to be very precise. We have to plan ahead. And I could think about planning all of this stuff, but I would need to make sure that I also have a value in some register that will tell me, yeah, but you've got to jump over this line. The point is that even though this is just a string of numbers, it still represents our if and our else. The check happens here. So this is where we check. This is the condition. This is where we check if R3 is equal to R4. If they are true, that's what we do here. We store register 3 to FF. So that's the if is true part is true. And if the condition is not true, then we come down here into the else part. And that's what we see here. with printing register 4 and jumping over line 25 by jumping to register 5, which stores the value of 26. Oh, I said 26, 26. So here is if the condition is true again. R4 minus R3 is equal to 0. We come here. Here's where we skip the then part if we've already done the else part. It's just a few lines of code, but it implements this idea. One thing you might notice, of course, what is actually this code doing? There's a shorter way of doing what we want it to do because, well, I could have just printed R4 here because they're equal, which means that really all I'm doing is printing R4. So I'm not doing anything particularly complicated here, but I'm using a make-believe if statement to just show you how this type of thing works. We're going to do something that's not make-believe here momentarily. But I want to show you one more operation, which is jump positive. It's the exact same as jump 0, except the instruction code is D1101. The next 4 bits tell you the register that I care about. And then you're checking that that it's equal to 0, but we're checking if it's positive. And so if it's positive, I set the program counter to the memory address here. Otherwise, I just carry on. So if register D is positive, I'm going to go to this particular memory address, which here I said was 88. And if it's not, I just carry on in the program. In this particular case, I could have a program like if R3 is greater than or equal to 4, print R3. Else, we know in this case that R4 is bigger than R3, we print R4. So slightly different program. You're going to notice it looks so similar. So we load into register 5 the value 26. We're still going to subtract them. So we're going to set register 2 equal to R4 minus R3. If R4 minus R3 is positive, well, we're here. So we know that R4 is bigger than R3. So if I call jump positive on register 2, we know that register 2 is positive, which means register 4 is bigger than register 3, and we're going to jump to line 255. 25, what do we do there? We print register 4. That's what store register 4 into FF does. So notice in this particular case, we check the condition, and then the else part happens here, and then we halt. The then part would happen if it's not the case that register 2 is positive. So register 2 is not positive when register 4 is not bigger than register 3, which means that we're here. And if we're here, then what do we want to do? Print register 3, and then exit the program, so jump over the else part. So it's the same type of operation. Here's if the condition was false. Here's where we skip the else. Now here's an opportunity for me to ask you another question, though, which is, we've done a lot of operations. We can even multiply by a power of 2 to the k with a built-in operation, but what if I want to multiply by 3 or 42, or I want to have two numbers that are input, and maybe I even want to write a function that multiplies these two numbers together. How is it that I could do that? Say, for example, I've got two numbers stored in registers 2 and 3, and I want to multiply those two numbers together. I'll give you a hint that I will allow you to use other built-in operations, so we have addition and subtraction available to us, but how does that result in multiplication? What I'm really asking you to do is call up your brainwashing from your primary school mathematics teachers. So I know, for example, that you know that the mitochondrion It's the powerhouse of the cell. And I also can trust universal authoritarian education to do a pretty good job of telling you that multiplication is repeated addition. AKB, got it? Good job. What does that mean? Well, it means if I want to multiply 3 times 5, what I'm really doing is adding 5 to itself 3 times, or adding 3 to itself 5 times. But I could represent a multiplication function as repeated addition even with like a Python function. So I could have a function, I don't know, I'm thinking I'm multiplying R2 and R3 together. It's not going to return anything because I'm just going to print it. And I could have this function that sets R1 equal to 1 and R6 equal to 0. And then what I'm going to do is I'm going to repeatedly subtract R3 until it hits 0. So while R3 is not equal to 0, I'm going to subtract 1 from it. So like if R3 is 5, my final answer here is R6. And so if R2 is say this is 3 and this is 5. While this number is not equal to 0, well, I'll say add register 2 to the answer and then subtract 1 from register 3. So as I go through this, register 3 would then be 4 and register 6 would be equal to 5. Or, excuse me, it would be equal to 3 because register 2 is 3. Then I would subtract 1 again, and I would continue subtracting 1 from register 3. And what we're doing is essentially getting it down to 0. Each time through, we add R2 to register 6, and then register 6 finally stores the answer. This was our mystery function from like when we introduced the concept of, yeah, we've got a Python function. How on earth could this function be represented as a string of ones and zeros? So I'm going to show you. We're going to implement this in Xtoy. And I'm going to place it not at starting at position 1, 0, but I'm going to start it at address 3, 0. And the idea here is to take the exact same premise as what that Python function of doing repeated addition was actually doing. So I'll say 7101 sets register 1 equal to 1. And we want to set register 6 equal to 0 too. I'm also going to save something because, well, let's do 317600. So those are just setting 2 values. Line 32 is going to store into register 5 something, and I'm going to hold on to that here for a moment. And the idea is I want at 3.3, I want to say, is it the case that register 3 ever gets equal to 0? So you can see over here, this is our branch 0 check. It says if whatever the register that I'm looking at is equal to 0, then we're going to jump the program counter. I will tell it it needs to go somewhere. Now, I'm not ready yet to set where that place is, because what I need to think about here is, in this particular case, you know, this is the case when register 3 is not yet 0. And if register 3 is not yet 0, well, this is inside our for loop. So when we look at our bizarre Python representation of a multiplication function here that's not allowed to actually do a multiplication, what am I doing each time through? I'm adding R2 into my final sum, which is R6, and then I'm going to subtract 1 from R3. So when I do that, well, those are the 2 steps that I need to take. And so what I want to do is set register 6 equal to itself plus register 2. Okay. And you'll notice that all got updated here. So we're inside of our for loop now. I'm setting register 6 equal to the sum of itself and register 2. In the next line, I want to subtract register 1 from register 3. So subtract is instruction code 2. And I'm going to say register 3 is equal to register 3 minus register 1. So register 1, remember, is just equal to 1. So it's storing this value of 1 for me. So every time through the loop, I'm decreasing the value of register 3 because I've just added register 2 into register 6. And you might not believe that this is even going to be a multiplication. And if you don't, that's fine. Guess what? I'm going to show you that this is a multiplication, but we need to figure out how to run it first. The point becomes, at this point, this is the end of the for loop. So if this is the end of the for loop, what I need to do is I need to jump to a specific place. And the specific place that I want to come back up to do is to actually perform the test. So the test that I want to run again is to check, is register 3 equal to 0? Because I want to keep looping until it's the case that register 3 is equal to 0, which means I want to use the jump register, which is E. I know that's what I want to do. And I would love to jump to this particular position to perform the test. But the problem is that this doesn't actually contain, when I do the jump, I'm jumping to the value of a register. And so it's the register that needs to contain the value 3, 3, which means I'm going to jump to the register 5 and everything else is ignored. So I'm going to go to the value of register 5, but register 5 has not been set. So I need to set register 5 equal to 3, 3. And now register 5 has that value, and when I go to register 5, it's going to take me to memory address 3, 3. And what's nice about this is that then this means that after all of this looping is over, this line, at this point, we are at the end of the for loop. So if I'm here, then I know what I want to do, which is to say print register F, register 6. Print register 6 to standard out. And in this particular case, I want to halt. Well, it's not letting me carry on, but so 3, 8, halt. And there's only one thing missing, which is that I neglected to say at the start of the for loop, I need to check, is register 3 equal to 0? And if so, I need to jump somewhere. When register 3 is equal to 0, I want to jump over the for loop, which means I want to go to this particular line, which is 3, 7. And this is a completely different way of thinking about programming entirely, and I know that. But the idea is it's still ultimately representing the exact same idea. It has two numbers in registers 2 and registers 3. It's multiplying them together. It's writing the result into register 6 and then printing that to the console, and then it halts. You need, of course, to see a demonstration of that, but the problem is that we want this to be a function. We want this to be a function called multiplication or multiply. And we want to say, it takes as input registers 2 and register 3. And it stores the product of the numbers into register 6. And then it writes the result to the console and standard out. We want all that to be the case, which means that we want it to be a module. We want to come back to this absolutely fundamental concept that we've seen throughout the course of a function being a building block or a module, which means it is reusable in a lot of different contexts. And if it's reusable in a lot of different contexts, that means that it should be able to be called by whoever needs it, right? But the problem with that is, what does that even mean? And it means that you might notice we've covered all of our instructions, add, subtract, and, XOR, shift left, and shift right, we've looked at all of the loading and storing to go back and forth between the registers and the memory. We talked about halt. We've talked about checking if something is 0 or positive, and we talked about jumping to a value is stored in a register. But there's one other code that we haven't seen, which is register or code F. And code F is going to allow us to actually have a function, and it's called jump and link. So it will allow us to jump to a particular place, but it also is going to have a bookmark associated with it. And this is inherently what we are doing when you're in func main or def main and you start executing lines of your code, and then you encounter a line that calls a function. When you call that function, you want to remember where you were so you could come right back to where you started. So you want to form this loop. And then you maybe call another function, but you want to remember where you were so that when the function is finished, you know to come back to this particular line of the code and continue on executing. So this is a simple idea, but it's a powerful one. And the idea is jump and link is going to jump to an address, but remember where you were. So instruction code F says, set the program counter to whatever these 8 bits indicate. So I just keep using this 88 RAM address, and we're going to jump to that particular place. But I'm going to store a bookmark in register D. So here, register D is F. Register F is going to, in this particular case, remember where I was when I was running my code. So I've got my code here. I call the function, and now register F is going to remember that it needs to eventually come back to this line of code, which means that in the meantime, I'm going to jump to this piece of code, which we're thinking of as a function. The code is going to execute, and then when that function is finished, now we have a concept of what it means for the function to return. It means literally return to another place. Like we can think of it as returning a value, sure, but you can also think about it as returning to a place somewhere else in our code. And that returning to the place somewhere else in the code is why this bookmark in register D is so important, because it will remember where we were when we called the function. Let's see that in action. So I want to come back to xtoy and look at the function that I have, and I'm going to call it function multiply. Notice if I don't use a hashtag as a function comment, and I just use the function keyword, it gets highlighted nicely, so that's good. And inputs here, registers 2 and 3. We store the product in a register 6, and we write that result to the console. Everything's going to basically be the same. We're going to see register 1 is equal to 1, register 6 is 0, register 5 is 3, 3. We're going to have our for loop here where we continue executing this until such time as register 3 becomes equal to 0, when we're going to write our final sum, which is the product of registers 2 and 3. And we're going to write that to the console, and then we're going to halt. The problem is, if I ever went to line 3, 0, the program would just stop, but we don't want that. What we want is we want to jump back to a particular place. Okay, so we don't want to just stop the program. We want to return somewhere. And this is why we need to specify one more little thing, which is the return address of where to go when the function is finished. And I'm going to use for this function something that is a good practice in general, is just to use a return address of register F. Whatever our final register is, that's where I'm going to go back to. So I'm going to say I could do EFAB. It doesn't matter because everything's going to get ignored. Probably it's nice to say EF00. So this line, as simple as it is, says, this tells me where to return to. The function needs to return. It's telling me where to go to in the code. So now this piece of code becomes something that's completely self-contained. As long as R2 and R3 contain what I want to multiply together, R6 is going to contain what it is that we have at the end of that, and it's being written to the console too, and then I'm going to go to register F as the result of this. I will show you then how this will work. So let me rewrite the code that we had previously. So let's set register 2 equal to 5, and let's set register 3 equal to 3. So those were the two numbers that I wanted to multiply together. Then I want to call the function. And so how is it that I'm going to call the function? You can think about this as, this is a program called multiply two numbers. Okay. And so this is like the main part of my program. It's going to set two numbers, register 2 and register 3 equal to 5 and 3. I also could do the same sort of thing where I just set 8 to FF and read it into the console or from the standard in. And I could also do 8.3 FF. So read in register 3. That would make this program even stronger. But regardless of how I do it, then I want to call the function. And I can call the function with F is jump and link. Remember, where is it that I want to come back to? It's register F. So F is the next hex digit in this instruction, because it'll tell me where I'm going to return to. And it's going to store, at this point in time, register F is going to equal 13. So it'll remember my bookmark to come back here. And now I just need to tell it where to jump. So where it needs to jump is the next two digits, which is 30. So what's nice is, again, I get the comment that tells me register F is equal to PC. Technically, it's going to be PC plus 1, but go to line 30. And so now, register F will store 13. And that's good because when I say go to RF here, we're going to see it come back here. And what is it that I want to do now? Well, I could get, I could halt the program here. I even like the idea of making this a little stronger and saying, let's not write the result to the console here. Let's not muddy the concept of returning a value, which is register 6, and writing to the console. So instead, I'm just going to get rid of this line entirely, and I'm going to make this 3.7. Okay, so if it's ever the case that register 3 is equal to 0, register 6 is going to store the product that I care about, and I'm simply going to jump to register F, which is going to take me back here. So before I halt, what I should really do is print here, and then I will, in line 1.4, then I will perform my halt. Notice when I called this program multiply two numbers, it automatically gave me the name of the program up there, so I can quickly save it. But what I really want to do is run this. So I want to load in, let's not do these. I want to load in 5, and I want to load in 3. And the product of those two numbers in base 10 is 15. We know, of course, that the number 15 in decimal is just 000F. So that's what I should see get printed to the console. There's two ways of doing this, the fast way or the fun way. I'm going to show you what happens when we step this forward very slowly. So we're going to first read in 5 and 3. Those get read into registers 2 and register 3. Now's when the fun begins, because we'll have FF30. So register F is going to store my return address. When I SIP this, register F is going to get updated. But meanwhile, the program counter is going to fly over to 30. So you'll see that when I step. Now register F remembers the bookmark. It knows that I want to eventually come back to line 1.3 of the program, which is what we said before. So eventually we want to come back here and print the value stored in register 6. In the meantime, we have to execute the function. So register 2 and register 3 hold the values I want to multiply. When I step it, you'll see register 1 gets set equal to 1. So far, so good. Register 6 is going to get set to 0. That's not technically necessary, but we didn't know that. Register 6 could have already had a value, so we're going to 0 it out. And then we're going to go through the process of performing the loop. So 7533 says store memory address 33 into register 5. So you'll see that is going to get updated there. And now we do the loop. So we say jump to register 3. If it's equal to 0, if register 3 is equal to 0, jump to line 37. Now, we can see that register 3 is not equal to 0. So what's going to happen? It's going to enter the for loop by going to line 34 instead. So when we step it, we see 1662. What does 1662 do? It adds register 6 plus register 2 and stores it here. Register 2 is 5, register 6 is 0. Add them together, you get a 5. Then subtract. So 2331 says take register 3 and set it equal to register 3 minus register 1. So all this is doing is decrementing register 3. So we've added 5 into register 6. We're going to subtract 1 from register 3. Then we have E500 that says jump to register 5. Register 5 has 33. So this takes us back to the top of the loop. The top of the loop says, is register 3 equal to 0? No, it's not. So because it's not yet 0, we're going to go to line 34 and we're going to do it again. 1662 says set register 6 equal to register 6 plus register 2. Now this is going to be equal to 10, or A. 2331 says subtract 1 from register 3. Now it goes down by 1. E500 says jump to register 5, which takes us back to the top of line 33. And then we say C337. Is register 3 equal to 0? It's not yet. Not quite. So instead we're going to carry on. 1662 says set register 6 equal to itself plus register 2. You add A plus 5 and you get F in hex. So that's the number 15. Take register 3, set it equal to register 3 minus register 1. Notice what happens now. Lo and behold, register 3 is equal to 0. Our repeated addition is finished. We're now going to jump one more time back to register 5. So we're coming back up to line 33. And now we say C337. All right, is register 3 equal to 0? It is. So what do? We jump to line 37. The for loop is over. And this line says jump to register F. Register F stores 13, which is where we wanted to return to when the function is finished. And the function is very much finished because register 6 stores our result that we care about. And so we come back to 96FF. And when we step it one more time, that gets executed. Oof gets printed, which is our value of 15. And the program halts because we're at 0, 0, 0, 0. So we now have a functional program that calls a function to multiply two numbers that are given by the user, places that value into register 6, and then prints the result back in main to the console and halts. It's not a fancy program, and yet it's doing the foundational work of what we have seen at the start of the course. And I could, of course, reset this and run it quickly. You'll see it runs quickly because the delay here between steps is set to be small. That's a parameter that you can also update here. So this is nice because it means we can even measure the number of steps that are required to be taken by different programs. Okay? That's going to be useful when it comes to timing programs, which is a hint about what we're going to do next time. In the meantime, I'm just going to say, you could give me any two numbers that you like. We could take the dreaded number, and we could take some other number and add them. And I could go to, run this, and you can see them. I thought I added them. And I could come here and I could go through the process of stepping through. And now at this point in time, we have a lot of subtractions to perform. And the reason why is because we took larger input numbers. So you can see register 3 here is containing the thing that we're subtracting. So every time through the loop, we're subtracting 1 from register 3, and register 6 is continuing to get added to by whatever register 2 is. So the terrible number is getting added in, although it means something different, I guess, in base 16. It's getting added into register 6, and this continues going. And I can run the process, and you can see the looping happening over and over again. And I've given it some large numbers with a sizable delay. So it's going to take some time. But the point is, register 6 is repeating up, is racking up these repeated additions of register 2 into them. And every time I add in one value of register 2, I'm subtracting 1 from register 3 so that I finally get this final multiplication. We're finally in our last couple of loops. And at the end of the day, we get 44CD printed to the console. What number is that? I don't know. 44CD is 17,613. And the numbers that we gave it were 0067103 and 171. So if you do 103 times 171, the product of those numbers, I hope, is what happens when we just multiplied those numbers. Okay. Sadly, I can't remember what the product was, but that's what happens when you introduce two other numbers into your brain. The point is, this is producing a multiplication of any two input numbers that you would like. And the idea here is we're starting to see that even though this is very simplistic, and each of these instructions is represented behind the scenes as a binary string of ones and zeros, we're able to actually call a function. Real assembly language instruction sets are not that much more complicated than this. Real ones will have more instructions built in because Xtoy is limiting us at 16 almost to show us what is possible when you only have 16 built-in operations, and that's nice. But real instruction sets for assembly language are going to have more than this. But at the end of the day, they're going to share the same type of spirit. And the point is that assembly language is simple, but it's powerful. In the case of video games, there are a couple notable examples of people who had a lot of success working directly in assembly language at a time when memory was at a major premium. These days, we have so much RAM on our machines that we don't have to care so much about like digging into the details. And this is why we've seen a rise of programming languages like Python that are very inefficient because computers have gotten faster and the memory has gotten cheaper. So when we're presented with a language like Python, there may be much simpler conversions of our code to the details to the assembly language or the machine level itself. And part of what makes higher level languages closer to human language slower on the whole is that this symphony of conversions is done automatically for you without you having to pay attention to it. And if you get a lower level language like C, you get a lot more control. You get closer to the machine itself, and that's why languages like C tend to be faster for the same task. And there's a dark secret that Python actually implements a lot of C automatically behind the scenes, and things like NumPy are essentially just a nice, pretty presentation of something that's actually implemented in a very low-level language because, well, it's faster. But that's the topic for another day. My point is, if you really want the fastest code imaginable, well, I guess you could learn to be an assembly language programmer. And that might seem like a ludicrous thing these days, but the point was at one point in time, that very much was not. And as I said, in the case of video games, there's notable examples. Chris Sawyer wrote essentially all of Roller Coaster Tycoon in the late 1990s in x86 assembly language. And so you wound up with a very powerful video game because it was constrained on the amount of memory that you had. but everything was hyper optimized because he had control literally at the register level. And on the music side of things, something that's near and dear to my heart is David Wise wrote the entire score for the Donkey Kong Country games that came out in the mid 90s, all in hexadecimal. So he wrote the music literally on this level, or the code to generate the music on that level. And that's why he was able to generate music that had so many layers in it in those games on a computer that had, the game only had 4 megabytes of storage, and the system itself of the SNES only had 128 total kilobytes of RAM. So you're in this very constrained memory environment. It allowed you to do something very creative if you could get your hands dirty there. Of course, these days things are quite a bit different. And yet, appreciating all of this and understanding the foundations of computing is still vital to having like a complete understanding of what actually is going on. My question, though, is now that we know how this works and we want to wrap up the course, what should we do? Like, I want to use Xtoy to write a program to do something, right? Something real. What is it that I should do? What would you vote on that I do? I guess we could do the entire course. Do the entire course in assembly language. I'd be impressed if somebody tried that. What should we do instead? Do a loop? Yeah, but let's be a little ambitious. No one has any ambitions. AKB saves the day. He said GCD. That's my exact thing that I want to do. So when we started the class, at the very beginning, what did we look at? We looked at ancient Greek algorithms, and the idea is, even though this is like the simplest thing you can do with code, there's still beautiful higher levels of understanding that you can attain from doing this, which is, why do we care about algorithms in the first place? You know, whether or not AI exists, regardless of what era we're in, we're always going to care about algorithms. And this goes back to all the way to the ancient Greeks, where they're not even dreaming of computers, but they're thinking of faster ways of performing arithmetic computations. And so rather than do the whole course, why don't we instead go back to the foundations of the course? And I will convince you that we could do the whole course, but we're just going to go to where we started. And where we started is with these ancient Greek algorithms. And in particular, where we started was with a nice straightforward algorithm for finding a GCD. And then this almost mystical, beautiful, elegant Euclid algorithm for finding a GCD that we showed in Python is much, much faster than an approach that we might try by hand. The question becomes, like, are we going to be able to see that here? If for one, am I even going to be able to fit a program for writing 2 GCD algorithms into the pretty constrained memory space that I'm given, where I only have access, to these addresses from 00 to FF. That's only 256 addresses, which is not very much. It's where I'm going to have to store the entire program, as well as anything that I need to store along the way for that program. And it turns out that not only are we going to be able to store it in that amount of space, and not only are we going to be able to measure the performance of these algorithms and hopefully see the same thing that we saw at the very beginning of class come up yet again, it's also going to give you the opportunity to do this exact same thing for our prime finding algorithms. So we have a prime finding algorithm that ranges through numbers and says, is this number prime? But we also have a prime finding algorithm that's based off this beautiful sieve of Eratosthenes algorithm that's like 2,400 years old that allows us to find primes much faster. And at the level of Python, you're able to actually measure that. You may be surprised, but you're going to be able to put the entire prime finding algorithm for like the sieve of Eratosthenes also into this framework. I think that's pretty neat. You will be amazed if you're able to do that. So this is, from my perspective, the perfect kind of capstone on a course like this, which is to actually implement all this, something that's reasonably sophisticated at the level of assembly language. I don't know of any better exercise for your computational brain than that, to fully appreciate like what a computer really is. And then the question is like, does that mean everything can be done in ones and zeros? Of course, yes. And that's what's going on behind the scenes. And if we had enough time, Sarah wants to do Conway's Game of Life in assembly language, go for it. I'll let you do that. I'm not going to do that one on stream. I'm going to leave that exercise for you. But I would be impressed if you did it. You're going to, of course, have to handle the visualizations and so forth. And you're going to need to work on a computer that has a lot more memory than just 256 addresses. That's not going to allow you to draw very big patterns. But yes, of course, you absolutely could do it. And that point is critical because it means if anything that a computer can do is ultimately just something this simplistic, how powerful are computers really? And what are their limitations? And that's the question after I implement some GCD algorithms next time. So I will try and quickly go through, here is an Xtoy implementation of me doing the same thing that we've done throughout the course. Here's a code along. You can follow along if you like. It's assembly language, so it's challenging. But it's definitely something that we can do. And then I'm going to take this question and run with a little bit next time of saying, yeah, but what are the limitations of computers? If all they're doing is manipulating ones and zeros, that means that they can't be infinitely powerful. And that's maybe something that might go against what your current thinking of modern computing is, given how powerful computers have become. But it turns out that there are problems that computers are never going to be able to solve. And they're reasonable questions to ask that we're not going to get an answer to. And all that is what is going to take us to the dark heart of computer science. But all that's going to be for next time. And I hope to see you then. And until then.